Maybe it's the mistake of my secret button. Okay, yeah, so fortunately I have good student realize this. And it happened long time or no? Okay, this is 3, this is 3, and this is 3. Okay, and the last one is, and the last one, no, the whole class so far. Wow, David. Wow. Well, okay, sorry. Now, the last one is a cone, no? This is a fee also, radio 3, and this is a cone. It's a cone. Yeah. And it's a cone. Actually, it's double cone, no? How do you know? Because no square root, no nothing. However, this restriction indicates us que no that part. Okay, so now, using my imagination, common sense, my solid is formed by something like that. Okay. Let me try to do my best. We have here one piece of the sphere. We have here one piece of the cone, lateral, and we have here one piece of the basically my solid look like that. Cone, sphere. And a sphere is invisible, that part, like that. It's like a, you know, a little bit hollow. No hollows, you know, it's, I don't know exactly pronunciation in English, but it's like a, well, you see now in 3D, in GeoGebra. So to make more clear the impression of the 3D, I do in this line. So this line is, I suppose, is like that, I suppose. Do you understand the solid or no? This is a challenge, you know, understand the solid. But let me try in GeoGebra to illustrate you. Okay, there you go. Two sphere and cone. Cone. Do you see? Do you see? Do you see? Look. This is the my solid. Do you see the bottom part? It's a little bit. Okay, let me show you. The surface. We have different surface. This is the top part surface. Okay. This is the bottom part surface. The lateral is this. You see? Concave. Es the name. Concave. Es the name. This is the wall of the cone, and this is the top part. So it's concave. Everything is concave. Concave down. No? Okay, well, let me try. This is surface. Okay, so complicated for you. But this is the cone. Boom. In yellow, you see, and green. This is double cone. Okay, cool. And this is the sphere, no? You have two spheres, no? This is sphere, and this is sphere. Two spheres. Okay, two spheres and one cone. Because you are doing in this, nobody understands very well the solid. You understand when you are doing surface. It's a thing that you don't know. But I promise in the test I put similar example. Okay. Do you understand the solid right now or no? We come back to the web. Come back, come back, come back. Come back, come back. You understand a little bit, sorry now. Cool. You see whiteboard? Okay, then, to say I understand. Well, no, I don't understand. To understand much better, we need to the view. The floor plan is relatively easy, XY. And another lateral view in 2D, it maybe has the famous exit 2D. Bueno, es obvio que the view in the floor plan is formed by two circles. Yes or no? And the radius 3 and 4. Okay. And the lateral view, no. The lateral view is, we have one circle or semicircle, radius 4. We have another radius 3. And we have the famous cone, same cone. Okay, and this is somehow the view of our solid. No? I see a little bit, not too much. Cool. Now, suppose que I dare to set up the triple integral. 1, 2, 3. Remember volume, integral function 1, and the order is always the same. Rho, the phi, the theta. And the Jacobian, don't forget, is rho squared sine phi. And you copy in this order the differential. The rho, the phi, the theta. Okay, the challenge is rho, que is the first integral. Go, from. You can see a little bit in the 3 dimension. Is my solid start here and end here. It's one possibility. Another possibility, in my opinion, is using the lateral view in which my rho start here and ending here. This is my solid, that one. Entonces es 3, 4. Clear or no? 2 sphere. Clear or no? Now phi vary from, this is the confusing part, guys. Phi is measured from z-axis, 0. This is phi 0. And this is phi pi over 4. But when you integration, you're extending in this direction. And finally, theta you see more clear in full plan. Okay, from 0 here to pi. Because it's the full circle. Okay, and the answer then is putting Wolfram alpha, and the review, no, the review I solved for you step by step. 37 2 minus radical 2 over 3 pi. That's the final answer. Cool. Everyone follow me? Everyone understand very well or no? Cool. David said, no problem. Okay, let's move on to the one more example. And that's it. And that's it. See, we have time extra. We start review. No, sorry. I have two problems of the Illustrate center of mass application, the double and triple engineer application. No review. Okay, example 3. Example 3 is different a little bit. You will help me as always, guys. This is the solid volume again, volume again, volume again, volume again. Si ese más, entonces hay specification the density function, ¿no? Entonces now T. Entonces the question is, well, entonces I using to compute the volume, I can use double integral or triple integral, both, of course, both, but the organization is different. No? You see in double, we are seeing now in triple, but in the review package, we are doing both ways, maybe. Suppose 1 over radical 2 is this first surface, and the second surface is x squared plus y squared plus c squared equal. And that's it. Okay, it's the solid bounded by two surfaces. Entonces no limitation, positive, negative, x, y, and z. Help me, guys. What is the first surface? Number 1. What is the name of this surface? C equal constant. What is that? It's a plane, obviously. It's a plane parallel to the xc axis. Okay? So I suppose, using my imagination, one specific 1 over radical 2, que es radical 2 over 2, no? Radical 2 over 2 rationalization, que is approximately 0.707, well, in this distance, I do the plane. But this is a sphere, it's obvious. A sphere, radius 1. Entonces now I suppose que you, let me try to do my best. You. Okay, this is 1. This is smaller. Entonces now, no, wow. This is a piece of the sphere. Okay, the plane cut off here. Okay, this is my solid. Okay, my solid look like that. This is a, it's a curve. Okay, when you projecting in the XY plane, you see it look like a circle, no? Wish. Circle. Okay. So not important to have super accuracy idea in 3D because it's complicated. However, it's to support this idea we are doing 2D. 2D. Remember, in spherical, I highly recommend 2D. For plan, and another 2D, lateral view. The famous XC and the famous XY. Now, it's obvious que it's a circle, yes, it's a circle. I have no idea what is the radius of this circle. I have no idea. No, I have idea. look, manipulate the equation. No? CC is equal radical 2 over 2. When you square, you have x squared plus y squared plus 1/2, no? Equal 1. Therefore, x squared plus y squared is equal to 1 minus 1/2, que es 1/2. Now the radio is square root 1/2, que es radical 2 over 2. It's obvious que es the same value of the C, of the plane. C equal radical 2 over 2. Cut off the sphere and one circle, que the radius is radical 2 over 2, radical 2 over 2, radical 2 over 2, and radical 2 over 2. Okay, cool. This is my region. This is my region. Now the lateral view, well, it's different. It's when I do the spheres, okay, the radius 1, this is the original sphere, that one. 1, 1. And we have a plane, okay, cut off this, and the height is C equal radical 2 over 2. And this look like my view, lateral view of the solid. Okay. Okay. Okay, ready to set up the triple integral. In this case, a little bit complicated. It's a little bit complicated. Let me try. Triple integral. 1 to 3. Integral function 1. So we have rho squared sine phi. Jacobian. D rho. D phi. D to see the rho was complicated. And the 3D rho go from the plane to the sphere. But the sphere is easy. So to see more clear, you see here. Well, let me make a zoom to see more clear. You go to the rho of the plane to the rho of the sphere. So basically, this is the range of variation of rho. Rho of the plane is not constant. It's a variable because the rho here is different. You know? This is constant. So in this integral, the lower limit is a variable, but the upper limit is 1. So for sure, I go to the rho of the plane to the rho of the sphere, que obviously is 1. Yes or no? However, I am confusing because I need to find the relationship of the rho. But I know. I come back to the spherical, no? The C is equal to rho cosine phi, no? But C is constant in the plane, que es radical 2 over 2. Radical 2 over 2 is equal to rho cosine phi. You isolate rho, entonces rho is equal radical 2 over 2 divided by cosine phi, no? But either way, you can write, for example, rho is equal to radical 2 divided by 2 cosine phi. And this is the formula Okay, put it here in the row of the plane. Cool. Radical 2 over 2 cosine phi. So I'm not always happy that the limits are constant. Sometimes, no, depending on the figure, the limit is constant or variable, contain variable. Now the rest is easy. The rest is easy because in the lateral view I saw the phi vary from 0 to pi over 4. And pi over 4, you say always pi over 4? No, depending. In this case, because the coefficient is 1, so the coefficient is different, well, so you apply trigonometric. This is from 0 to pi over 4, and this is from 0 to pi. Cool or no? Okay. In my paper, I forgot to compute that. Okay, it's not important. The important is the setup. In the test, yes, you have to compute it using orphan alpha line. It's very complicated. Any question on this? So, when I want to spend the rest of the time doing applications of the triple integral. Because always volume. No. We can compute, for example, center of mass, center of gravity, centroid. Another application, the only thing you should do is, well, modify the integral function. Suppose find the center of mass. Center of mass. Of this figure. Okay, this figure is a parabola, no? Let me see. Yeah, it's a parabola like that. Okay, the equation for this parabola is y equal 1 minus x squared. Entonces my solid, guys, is this. So bonded. It's bonded by this parabola, and x-axis. Okay, basically is that point is 0,1. That point is 1,0. That point is negative 1,0. And of course, this axis, que es the x-axis, is y equals 0. So this is my actually it's not solid. It's a lamina, because we are solving using double integral, and this is possible in engineer when you suppose that the figure that you are working, one dimension is negligible. Suppose a big lamina is very thickness, aluminum, you need to find the center of mass. So you ignore the thickness, because it's negligible. So suppose it's big, but that part is considered negligible. And you need to find the center of mass. Where you get a center of mass. Okay? And what is the formula? Well, the formula is the x of the center of mass is the momentum in y divided by mass. M is the mass. Okay, this mass is, see, I need the density function, and y is momentum x divided by mass. The density function is given. Okay, the density function is given. Entonces, the density function rho x, y, I suppose que es 1. Entonces, si es 1, this is not center of mass, it's centroid. Because the difference in between center of mass or center of gravity and centroid is que you suppose que the density is maybe variable. Si es a function in 2 dimensions, and suppose that the top part is more density than the bottom part. So the center of mass is moving over, no? You know, but in this case, the density is uniform, is constant. Entonces now actually es centroide, ¿no? Es centroide es like a center geometrically, ¿no? Okay, cool, no problema. Okay, entonces let's do the double integral. So, 2 new things bring me this example. Part number 1 is que not always is possible in this application using triple integral. Sometimes using double integral when the one dimension is completely negligible in the figure. Number 1. Number 2 is the idea for the centroid. No? Centroid is equivalent to the center of mass under the supposition that the density is constant. No constant, sino equal. Okay, now the formula. What is the formula? Well, the M is the double integral in the region R. Okay, by the way, this is our region R now. Of the density function, okay, 1 dA. So actually, it's the double integral. This is 1. Cool. Entonces, well, I make a decision to convert to define the order of orientation. Remember, I prefer always in this order. So you integrate dy first, dx secondly, and you open the window and the iteration after that when you perform the first integral. So the first integral go from y0, the top r, to the y of the parabola, que is 1 minus x squared. And when you open the window in x, I go from -1 to +1. Right? And the answer is 4 order. This is mass. Of course, this mass is, well, this density is kilogram per centimeter square, because you neglect the 3 dimension, and this mass is just in kilogram. Either way, or pound, whatever, it's not important. Okay, now compute the ny. Ny is momentum. A momentum is, again, double integral in the region R, but you copy now x, que is completely opposite letter with the distance, dy dx. That's similar. The only difference is okay, now we have x, and you integration dy dx, and doesn't change the region, therefore it's the same limit, 0, 1 minus x squared. See, you continue in the same order of integration, and you are doing that, and the answer is 0. And make sense, okay, 0, because the centroid or center of mass, see, the density is constant, lie on the y-axis. I suppose, using my imagination, my logic, that the center of mass lie on the y-axis, because depending on the symmetry of the figure. Cool, right? Let's do it now. Momentum x, que es similar formula, ¿no? Double integral in the region per y. Now y, dy dx, and the limit stays the same region, and the answer is 8/50. Cool, we finish. Now, what is the center mass? Well, I come back. come back to the original. The center of mass is divide ny is 0 divided by something is 0. And the other guys is nx is 8 over 15 divided by 4 over 3. Okay, this is 2/5, 2 over 5. And 2 over 5 to have some idea, approximately 8.4. So the center of mass is parabola. Is located at one point here, guys. Okay, let me try to do my best. -1, +1, 1, this is 0.5, and this is a little bit down. The center of mass or centroid either way is 0.4. And make sense or no? Yeah, because that part is wider than that part. So the center mass is located a little bit below the middle point. No? Makes sense, right? Oh no, that's crazy. You understand very well the idea or no? Yes or no? You follow me or no? Okay, let's do it one more. In 2 dimension, and next time we start doing one in 3 dimension. And start review Monday important day. Okay, another example of the centroid or center of mass. Oh no, it's different. It's center of mass. Center of mass. But the density function is given. Is 1 plus 3x plus y. Wow. So it's not uniform. The mass is different in any point. And the figure, get the region, is a triangle. Triangle like that. 1, 2. Well, sorry. 1. This is going 0.2. And this is 1.0. Like that. This is my figure. I want to find the center of mass. Okay. So it's, by the way, I compute the line equation case y equal minus 2x. Okay. This is the region R. Easy. The mass. The mass is double integral in the region R. So the density function case 1 plus 3x plus y dA. Okay. Now, more specific in this problem, I integrate dA y dx because I want to integrate in this direction. So I go y from 0 to the y of that line. It's minus 2x plus 2. And when you open the window in that direction, I go from 0. Okay, y I omit the arithmetic, cal 1. You know that perfectly. The answer is A over 3. It's a mass. Momentum y. Double integral again of x multiplied by 1 plus 3x plus y. Specifically in our region is x times 1 plus 3x plus y. I integrate in the same order, therefore doesn't change the limit. Okay, now unbelievable, the answer is 1. Okay, and momentum x exactly the same, but it's y now here. is double integral, same limit, same region, but the integral function change. Now y. And the answer is 11 over 6. Okay, first of all, now finally, definition, center of mass is x hat is ny divided by m. With 1 over a over 3 is 3 over a. Boom. And y hat is nx divided by m is 11 over 6 divided by a over 3. Okay, the answer is 11 over 16. 16? Let me see, 11 over 6 times 3 over 8. It is simplification to 1, 11 over 16, yes. Okay. Super cool, right? Okay, guys, too much. So now, next time, next time we are doing the one more problem of the three-dimensional center of mass, and we start review. I send the review package. Elola, are you there?
Yes.
I am confused with your name. Your name is Lourdes González de Mendoza?
Sí.
Okay. Pero you using nickname Lola Mendoza. Carajo.
Yeah, I know.
I realized in the first test, where is this girl? But I forgot to ask you. But no. I make it my own conclusion. It was right. Thank you, everyone.
Thank you.
Bye-bye.